Okay, here today we are going to learn how to calculate the torque on a rectangular current carrying loop, which is kept in a magnetic field, that is uniform magnetic field. So this is the picture. In the picture, left picture, we have already seen a this a loop, a rectangular plate, say. So I'm going to denote this. So this is a plate, rectangular plate, okay, and current is entering from this side and leaving to that side again after traveling through the loop. Okay, so it is a metal plate which is kept between the two magnetic poles, that is north and south, so that the magnetic field is directed from north to south. Okay, and this is the front view we have taken. And if I see this picture from the right hand side, then it will be looking like this. So these are the magnetic field lines, and between the field lines, this is the loop. Okay, it is appeared as a thin line, thin green line. So there is a plate actually. Okay, so this loop is kept actually in parallel to the magnetic field. It is obviously visible from this right picture. It is parallel to the magnetic field. So we are going to calculate the torque on the plate right now. To get the torque, we have to first find the forces on various segments of the same loop. So I'm going to denote the segments at A, B, C, and D. We have already taken the DL1 vector, DL2 vector, DL3 and DL4 respectively along AB, BC, CD and DA. Okay. Okay. So what is the formula of the force? Formula of the force is coming from the Lorentz force law, that is I integration DL cross B. I is kept outside the integration because the current is taken to be uniform. That is why I is kept in, I is actually outside the integral. Okay. Now we are going to consider the force on various segment part by part. So if I see, if I going to calculate the force on AB, then we see that dl1 vector is actually the perpendicular to the magnetic field, right? From the front view, it is easily visible. The angle between the dl vector and the angle is 90 degree. Hmm? That means this cross product actually gives this cross product actually contains a sine theta between the dl and b. Hence, this sine theta is now sine 90 degree, and sine 90 degree is 1. That means this cross product is non-zero quantity. Second, the in BC, the DL2 is actually parallel to the magnetic field. The angle between them is 0 and sine 0 is 0. That means the cross product will give you 0 here. So there is no force on BC. So F equal to 0, right? Similarly, before going to CD, we can easily see that AD in AD, so DL4 is antiparallel to the magnetic field. Again, the angle between is pi and it gives 0. So the force on CD is also 0. And the last is the CD. Okay. So here you can easily see that the DL3 is again perpendicular to the magnetic field, and you will get that if CD is a non-zero quantity. So during the to calculate the force, we can easily see the contribution will be coming from only from AB and CD, because along those lines the line element DLs are perpendicular to the magnetic field. Since the magnetic field is taken to be uniform, so this the magnetic field can be kept outside the integration. right? Because it won't take part because it is a constant itself. So F can be written as only integration of dl I cross B. B is now kept outside, but I cannot bring B left side because it is a cross product. I cannot change the order. So the integration of dl is the full length L, that is B. Okay. So now we are going to compute the force on the current loop on AB can be found very easy way. So I L AB plus B. Okay. Now and force on CD also we can write I L CD cross B. Okay. Good. So now I have to bring the picture again in the next page so that I can make you understand better. Yeah. Okay. So now what I'm going to do, I'm going to take the some directions so that I can calculate well. Here in this direction, so to the left direction, I am taking x-axis. In vertical direction, I have taken y-axis. Oh, then according to the right hand rule, we know the z-axis is vertically upward. So z-axis is vertically upward. It is pointing towards you. Okay. So now we can write easily from this axis that LAB, that is in this direction LAB, is can be written as if the magnitude of the length is A, say length is A into I cap. Magnetic field is now pointing downwards, which is opposite to the y-axis. So magnetic field can be written as the B into minus J cap. So if I now going to calculate FAB, that is simple, right? I'm going to write all the things properly. So I LAB cross B. So LAB is I cap cross B minus J cap. So I cap cross J cap is K cap, and since there is an extra minus sign, so the force becomes IAB minus K cap. That means it is pointing along the negative x-axis. But we have already seen that the z-axis is pointing towards you. That means this force actually pointing vertically downward. It is away from you. It can be seen very easily in the side view picture. If in the side view picture, since you are looking from this side, the x-axis is pointing towards you. This is y-axis, and and since the z-axis in the front view is pointing towards you, that means z-axis is along the left side, and in this side, this is negative z-axis. So it is now we can see that the force, what we have already found, F AB is in the along the negative z-axis. So it is done. And the value we have already found magnitude, that is IAB. We do not need to calculate the FCD because we can anticipate the value in the sense that the LCD, here the line element is opposite to the line element, the direction of the line element along CD is just opposite to the line element of AB. So the force must be opposite to the AB, right? With the same magnitude because AB, the length of AB and CD are equal. So here the force in this direction along the positive z axis. So now we are ready. So we have found two forces. Both are having same magnitude, acting opposite to each other. And from the notion of the couple from class 11, we know that these forces constitute a couple, and the torque produced by the couple, okay, sorry, the torque produced by the couple can be found very easily. That is the definition of the torque is the force into perpendicular distance between them. And the perpendicular distance I have taken the perpendicular distance I have taken as b. This is the breadth of the parallel plate. So this line, the length is b. So that is f into b. And f we have already found. The magnitude of the f is I a b into b. So the torque becomes I b a b. And since a is the length and b is the breadth of the plate, so it becomes the area. So that is it becomes b a I. So torque becomes b a I. So we have to remember one more thing, one more important thing here. So this actually the force is computed for a single turn, a single windings around the square plate. But if there are n number of windings, then we have to remember the torque becomes so the total since each turn contains I, the total current becomes Ni because there are n number of turns. So for n number of turns, the torque becomes just I'm going to multiply by n, so it becomes BANI. So this is the torque. But we have to remember it is not at all a general torque formula because we have taken a very special case when the plate is parallel to the magnetic field. Okay. But now we are going to take a more general case where the parallel plate is not at all parallel. So sorry, the plate is not at all parallel to the magnetic field. So I'm going to draw the picture again from the front view. So this is the magnetic field. But now the plate is slightly tilted with the magnetic. So I'm going to draw the magnetic field lines first. And now we are going to draw the plate slightly tilted with the magnetic field. Okay. Now the plate is slightly tilted. So it is a front view. So there is a yes, it's a side view again. Good. And I'm going to take the angle theta here to denote the plate is making an angle theta with the magnetic field line. Again, I'm going to calculate all the things properly. So again, the force is acting along negative z axis. So okay, so first I'm going to I should draw the axis properly. So in the side view, I've already seen what are the axes are. So I'm going to write those again. So this is y. So in this direction, that is negative z axis, and x axis is vertically upward. So the force, okay. So the force becomes along the negative z axis as in the old case, the previous case. So that is in this direction, and this force along this positive direction. That's all. Okay. So now our task is to find the torque. So, but now the perpendicular distance between the forces changed. So the perpendicular distance between the two forces now, I'm going to designate those points. So perpendicular distance between the two forces. This is the line of force of the force given below, and that is the force. This is the line of force of the force given above. So at P. So the perpendicular distance is this distance, right? Okay, I'm going to, so the perpendicular distance becomes between the two forces is simple PQ. And since these directions, already we have taken this direction as B, this part is the breadth of the plate, and this is theta, and this is the alternative angle theta. Okay, so the PQ become F cos theta. Sorry, sorry. I should write PQ as B cos theta, not F cos theta. So PQ is B cos theta. So now we are ready. So again, the torque produced by this is F PQ, and that means B A I. This was the magnitude of the force into PQ, that is B cos theta, and that means it becomes B A A B cos theta, and that is B A, that is area into cos theta. So that is the torque. So this is the most general formula right now found for the torque. On a plate which is slightly tilted, the plate, this angle, please remember this angle, this is very crucial point to remember, that is this point, this particular theta is actually the angle between the plates, between the plate and the magnetic field line. Okay. So that is the formula for general case. But now we have to consider a more important fact to bring it in the formula, and that is much more important than this particular formula. That is, we have to consider the area vector into this picture. We know the area vector. Area vector is denoted the area, any area whose boundary is traveled anticlockwise. If it is traveled anticlockwise, the unit vector is taken upward. It is a convention you can take. So, and if this area is A, then A into n cap, A is the value of the area, and multiplying with the n cap, the unit vector is giving me the area vector. So this is the definition of the area vector. Area itself is a scalar quantity, but a vector quantity can be formed by the multiplication with this unit vector, that is called the area vector. Okay. So here we can see that current is moving. So I'm going to giving the direction of the current right now. This is a current. So if you see that you can take the area vector in any one of the side, it is depending on the on your choice. So I'm going to take the unit vector. So if you will see carefully, if you will see the plate from this side, okay, then you will see the current is actually traveling anticlockwise. And if you will see from this side, okay, this is the plate actually. So current is traveling from this side, the current is traveling anticlockwise, and from this side, current is traveling clockwise. So unit vector on the plate is n cap in this direction according to our convention. Hmm. So the so yeah. So I have to draw this properly. Okay. So this is the n cap. Now what I am going to tell you that if this is theta and this is this the full angle is 90 degrees, so this angle is obviously 90 degree minus theta. And I'm going to write the 90 degree minus theta as alpha. So the and so 90 degree minus theta as alpha. Alpha is the angle. So alpha is the angle between the n cap and the magnetic field line. Okay. So, but you can take the n cap in different directions, so does not matter. Okay. So that is the angle between the. Okay. So that is an say alpha, or you can take this angle also. Okay. So it is your matter. It does not actually matter anything in this calculation. But the one have to we have to remember that 90 degree minus theta is alpha. Alpha is the angle between the n cap and the magnetic field line. Okay. But if you will take, so I'm going to draw this again here. And this is the plate, say. So, yeah. And this is, you can take in this side also, there is unit vector. If you choose the convention, opposite convention, does not matter. Then this angle, you have to take the alpha. Okay. So again, yes. Okay, so this is the plate we are talking. So I have to draw it properly so that you can understand better way. So that is the plate. Actually, the plate is rotating like this. Yeah. Okay, so now you can take this also alpha. It is your choice. So if this is theta, okay, and this is 90 degree, then alpha becomes, what is alpha? Alpha becomes 180 degree because this full angle is what this full angle is 180 degree. So 180 degree minus 90 plus theta. So that is become 90 degree minus theta. The same thing. So I have shown that there are two ways to represent, that does not matter. So what we are going to see that I am going to replace the theta in terms of alpha in this formula. So the tau becomes B I A cos theta. And now theta can be written as 90 degree minus alpha. So it becomes BIA, that is sine alpha. If there are n number of turns, then the tau is modified with the fact that you have to multiply you have to you have to bring the n in the expression. So it is the full formula of the tau. It's a more general formula we have to consider here. So that is the tau. Good. But now, again, this we have to introduce another quantity in this picture, which is called the magnetic dipole moment. The magnetic dipole moment is defined as vector m. It is a vector quantity. It is defined as I into area vector. Suppose our area is traveled by anticlockwise, and then if it is anticlockwise, you can this is the area. It is traveled by a current anticlockwise. Then you can draw a unit vector on the area that is pointing upward. So the area into the unit vector is the area vector and multiply by the I is scalar quantity, is give the magnetic dipole moment. So this is the definition of magnetic dipole moment. So you can easily see, so okay, if there are n number of turns is here, then you have to multiply the whole thing by a n because there are total number of current is Ni. So the magnetic dipole moment is modified like this. Why I am telling this? Because the you can easily see the in the formula of general formula of the torque, you can already see this particular ANI is present. That means I can write the torque equal to Bm sin alpha. And M is pointing towards the so M is pointing towards the n cap, right? That means the picture becomes the picture becomes like this. So this is a B, and this is the n cap. So and this is the direction of the m cap. So it is also the direction of the m vector, right? So I'm not writing now n cap. I'm writing the direction of this is the m vector, and this m vector making an angle. So the m vector making an angle alpha with the magnetic field, and the torque is actually giving anti-clockwise. Sorry, clockwise. It is moving. So this torque produced by this magnetic field or the magnetic force is clockwise in clockwise direction because the plate is moving like this in clockwise manner. So we can write the torque vectorial form in two ways, either B cross M or tau M cross B, because we have found M is a vector, B is a vector, and sin alpha is there. Then this torque is a vector quantity. So either we can express the torque as a cross product of two vectors vectorially or in a different order, right? In the sense that we can express the cross product in two orders. So which one is correct? We have to decide first. So according to right hand rule, okay, the torque which is produced by the magnetic field clockwise is given from this one. If we apply the right hand rule, okay, then you will see the torque is actually rightly expressed by this one. Hmm? So you have to apply the right hand rule here with your finger, then you can see the torque is produced like this. So that is why we can take, so this is the right expression. So right expression is the general expression of the torque is expressed by m cross b. Now we can draw the correspondence between the electrostatics and magnetostatics here, and that is very important point and very important moment right now to draw this correspondence or to introduce the correspondence. The correspondence is, so in the electrostatics we have already seen the magnetic dipole moment is given by P. So electric dipole moment is given by P. Here the magnetic dipole moment is given by M. So this part here, that is electrostatics in this side, and that is magnetostatics in this side. So in the electrostatics part, the electric dipole moment, sorry, the electric dipole moment is given by P vector, and magnetic dipole moment in magnetostatics is given by M vector. Here is charge. The definition of the electric dipole moment is the magnitude of the charge into distance between them. D is pointed from negative charge to positive charge, and M is here. The charge is replaced by the current, and the D is replaced by the area vector. Okay. Next thing, the crucial thing, the similarity between the two formula of the torque. When an electric dipole is placed in an uniform electric field, the torque is given by P cross E. And when a magnetic dipole, that is a current carrying loop, is placed in a uniform magnetic field, the torque is given by M cross B. So these are very, very similar formula and similarity between the two spaces in the sense of two sections, electrostatics and magnetostatics. So ultimately, we have found the torque when a plate is tilted and whose area vector is making an angle alpha. That means the dipole moment, magnetic dipole moment is making an angle alpha with a magnetic field. Then the torque becomes M cross B. Okay. So this is a more general formula of torque when a plate is tilted, is kept tilted in a uniform magnetic field. Okay. So we will actually we will see in the latter video that how we can find the torque on a circular loop. Okay. A disk, say, when a when a current is passing through the disk along the boundary, instead of rectangular loop, we are going to consider a disc-shaped uh, plate which is kept in a magnetic field like this. So we are going to this is suppose that there is a magnetic field, magnetic pole, that is N and S, and when that is the magnetic field lines, and when a disk now is placed here, and the circular disk, okay, and current is entering from here and leaving it, then it will again similar with a similar argument given for the above case. We can easily see that the disk is also rotating because it will be having a torque produced by the magnetic field. Then we will calculate what is the torque on that. It is slightly more complicated formula or more complicated calculation than this case what we have already considered here. But the formula remains same. I have to tell the result. The result remains same. If there are n number of turns is here and this is the radius, average radius is r, okay, then the torque becomes simple when the disk shaped plate is kept in a magnetic field with n number of turns and parallel to the magnetic field, then it is the same formula we have. And when the disk is slightly tilted, that means is area vector making an angle alpha with the magnetic field, the torque, the formula remains same. Carrying current, carrying uniform current, right, in uniform magnetic field. Okay. So this remains same. So, but we have to remember the A is pi r square, and R is when there are n number of turns, we have to consider the average radius. That is much more crucial thing. That if there are n number of turns, R is the average radius. Okay. Okay. So yes. So let us stop the video here, and we will find this particular torque and how we will find the same formula. We will see later. Bye.